Hello, my name is Jun Hyung. The title of my project is Origin of Flat Energy Band. So I will begin by introducing what flat band is. So some special lattices exhibit dispersionless energy band. In general, most lattices only have dispersive energy bands, but some of these special lattices include Kagome lattice, Lieb lattice, and Dice lattice. Here I have uh, as an example here I have the Kagome lattice structure and its energy spectrum. At the top, the energy band is flat. Another example is the Lieb lattice. I again have the structure and the energy spectrum, and in the middle you see a flat band. But why is it so important to study flat band systems? It is because flat band systems provide a platform to study exotic physics, such as unconventional superconductivity, whose principal mechanism is not the electron-phonon coupling, which is the conventional mechanism, but it is the electron-electron coupling, which is manifested in flat band systems. Another is the fractional quantum Hall effect, which requires completely quenched kinetic energy, which is, again, a main feature of a flat band. And also a Mott insulator, which is a special system where it is supposed to be a conductor by conventional band theory, but it turns out to be an insulator. But then there's one slight issue with known flat band systems is that normally flat bands come degenerate, meaning they touch other dispersive bands. As an example, let's look at the Lieb lattice. The flat band in the middle is touching the top and bottom dispersive bands at the corners. And this is a problem because when bands are connected like this, they form one superband and it suppresses the flat effect. So we want to isolate the flat band. But how do we isolate it? Naive attempts to isolate flat band may result in dispersing the flat band. So it has been known that applying an external magnetic field lifts the degeneracy of flat band. So let's take the Kagome lattice as an example. The flat band is degenerate here with the dispersive band below it. When you apply an external magnetic field, this is what happens. The flat band, it splits into a few bands, but at the same time, the band which was flat now becomes dispersive. And in general, flat bands are so fragile that any modification can easily destroy it. So here is my objective. Since based on what I just showed you, it seems very crucial to understand what protects the flat band. So, and if I rephrase the problem statement, if you can engineer a flat band system, you should be able to identify the origin of the flat band. There have been many attempts to find a general method for engineering flat band systems. But so far, all the proposed techniques out there are conditional, meaning they are restricted to certain systems only. And the goal of my project is to find the general technique that doesn't have any restriction. And here's the method I will follow. So by studying the Hamiltonian, you can usually identify symmetries associated with various properties. So, and in fact, in recent work, we found a symmetry for lifting flat band degeneracy in certain systems. I will elaborate what this is in next slide. So we'll look for the structure of Hamiltonian that gives us the flat band. And based on this structural analysis, we can possibly identify a physical symmetry for the flat band. So the Hamiltonian takes a matrix form, and thus the analysis of its structure requires knowledge in linear algebra. So I will describe what we did in our recent work. So recently we reported on the identification of symmetry for isolating flat bands in bipartite systems. What is a bipartite system? It's a lattice composed of two sublattices where the members or sites in one sublattice only talk to the sites in the other. Here's an example called H5 lattice, which is composed of the two sublattices, which are the Kagome and graphene. And the Hamiltonian structure has this form where in the top left corner block, uh, it describes the hoppings from XY sites to XY sites. So it is hoppings within the same sublattice, the same XY sublattice. And likewise, in the bottom right corner, it describes the hoppings from ABC sites to ABC sites. Again, that's hoppings within the same sublattice. So for a bipartite system, these the diagonal blocks should be zero. So in other words, whenever you see a zero diagonal blocks, it represents a bipartite system. So in this work, we showed that the number of reducible rows in the Hamiltonian equals the degree of degeneracy at a given K and E. So for example, if at the given K and E, if there's no reducible row, it means there's no solution. If there's one reducible row, it means there's a non-degenerate solution at that point. Two reducible rows means doubly degenerate solution, and so on and so forth. So again, using this example of H5, if you choose your K and E at some point over there, there's no solution. So in your Hamiltonian, there is no reducible row. If you choose your K and E to be a point over there, um, the Hamiltonian should have one reducible row because there's only one solution at that point. And if K and E happen to be at this point over here, there should be two reducible rows because there's a doubly degenerate point there. And also at the center here, since there's a triply degenerate point, there should be three reducible rows in the Hamiltonian. So mathematically, we also found a way to lower the number of reducible rows in the Hamiltonian without destroying the flat band. So for example, you can lower the number of reducible rows from 3 to 1. In other words, you can lower a triply degenerate point to a non-degenerate point. So for example, again, in the H5 lattice, and at the center here, we have a triply degenerate point. By applying this method, we found you can lower the number of reducible rows and lower the degree of degeneracy to 1. So now the flat band is completely isolated. And what this demonstrates to us is that by studying the structure of Hamiltonian, you can learn something about the structure of the band, and you can possibly manipulate it as you desire. So the prescription we found is purely a mathematical operation, and we were able to link it to a physical interpretation. So and that meant that as long as you respect the symmetry, you can apply any kind of modification and still isolate the flat band while protecting it, while not destroying the flatness. So it seems like a promising avenue to study in a purely mathematical perspective, and we can possibly extend this work to our future research project. So we can extend this work to general systems, which doesn't have to be bipartite, and for finding flat band symmetry. So in our recent work, we found the symmetry for isolating the flat band, but now we want to find the symmetry that protects the flat band. And here is the outline. To elaborate, I will elaborate what the project will look like. So if your Hamiltonian is reducible for all k at a given E, it implies a flat band. Again, recall that the number of reducible rows equals degree of degeneracy. So if you have at least one reducible row, it means there is a solution. But for now, we will not worry about the degree of degeneracy. So as an example, here is, again, this energy spectrum of H5 lattice. There's a flat band at E equals 0. So for at E equals 0, for all k points, your Hamiltonian should be reducible. And especially at all points except the center, there should be one reducible row because there's a non-degenerate solutions. But at the center, there should be three reducible rows. Anyway, so this is the Hamiltonian structure of the H5 lattice. And you can easily see that by performing a linear combination between, let's say, the third and the fourth row, you can always reduce the last row. And this is independent of k. So for all k, you can reduce at least one row. Again, for all k, there's at least a non-degenerate solution, meaning there's a flat band. So now we can use this understanding of flat band in bipartite systems, and we can extend it to study general systems. And the reason is because we can view any general system as a perturbation of bipartite system. So as an example, consider a generic 3x3 Hamiltonian, where I labeled each entry by their row and column numbers. So we can view this as having this base structure, which is bipartite. Again, the diagonal blocks are 0, so it's a bipartite system. And now we can view these diagonal blocks having a perturbation, which are H11, H22, H23, and so on and so forth. So all we need to figure out is the relation between the base bipartite system and the perturbation, because we have a pretty good understanding of what about flat bands in bipartite system. So the question we will ask is, what kind of modifications preserve a flat band? And we'll first precise the mathematical rule, in other words, necessary conditions for flat bands. And based on the mathematical operation, we will try to come up with a corresponding physical interpretation. Potential impacts include, once you have a physical symmetry associated with flatband, you should be able to construct any flatband system with any desired ingredients. The reason I'm saying this is because for different purposes, you might want to have different types of systems, such as different system size or different types of atoms, and so on and so forth. And again, another potential impact is that you will be able to modify the system as you wish, while protecting or preserving the flatband. Usually imposing certain properties, specific properties, tends to perturb the system. So for example, isolating the flatband or controlling the size of gap or topological transition, and et cetera, et cetera. And by another potential impact is that by extending the method, you may be able to investigate other properties of band structure, such as the type of degeneracy, Dirac cone or quadratic band touching point. Possible challenges include the fact that the rule for general system may not be simple enough for practicality. And another is not being able to associate mathematical operations to physical interpretations. An alternative resolution for these challenges is to impose a restriction and finding a simple rule for a certain restricted class of systems only. So this was my research proposal. Thank you so much.